Hey everyone, welcome back to The Explainer. Okay, today we are unpacking an absolutely mind-blowing feat of software engineering. We're looking at the architectural blueprint for the OTR Open Video Model Platform. If you follow the bleeding edge of AI, but you're kind of sick of monolithic cloud services that just lock you into their specific ecosystems, you are going to love this. We are exploring how a team engineered a 100% local, fully offline AI video studio. And the real kicker? They designed the whole shebang to run locally on a single RTX 5080 laptop with just 16 gigs of VRAM. It's a masterclass in constraint-driven engineering, and by the end of this explainer, you're going to see exactly how they pulled it off.
All right, let's dive right into this blueprint. We're going to cover the local video engine, why audio is king, the model-agnostic spine, the 3 core pillars, beating the hardware limits, and lastly, the final assembly.
First, Section 1, the local video engine. We're talking about building a complete digital movie studio right on a laptop. To really wrap your head around this, think of this platform as an entire Hollywood backlot, but instead of sprawling across acres in LA, it's literally squeezed into a single laptop. The engineering constraints here are just staggering. Look at this definition straight from their design docs. A 100% local, offline, model-agnostic AI video engine built as comfy UI custom nodes. And remember, it's all running on an RTX 5080 with just 16 gigabytes of VRAM. Honestly, 16 gigs is barely enough to keep a modern web browser happy these days. So cramming a full multi-model pipeline into that tiny footprint completely offline, well, that requires an incredibly disciplined architecture.
Moving on to Section 2, audio is the king. It's the strict director of our timeline.
On this digital set, the audio track is basically the strictest director you could ever imagine. Master audio is frozen before a single pixel is ever rendered. It acts as the ultimate single source of truth. Video never, ever dictates the pacing. It just conforms to what the audio has already laid down. Because of this strict rule, the platform hits zero waste. The exact clip budgets, like down to the precise integer frame count, are computed directly from the audio ledger before any rendering even starts. It's a strict smart generation limit, meaning absolutely zero overgeneration. When you're in a completely VRAM-starved local environment like this laptop, you simply can't afford to render a single frame you aren't actually going to use.
Section 3, a model-agnostic spine. Think of this as having interchangeable actors for every single role. This is where the platform's core philosophy really shines, totally avoiding dependence on any single AI model. Let's contrast the two approaches here. On the left, we have your traditional monolithic AI engine. One primary model dictates absolutely everything. It's highly rigid, and if that big model struggles with, say, a specific type of tracking shot, well, you're just stuck with it. Now, over on the right, the OTR way, pluggable adapters. No model is primary. You, the user, pick the specific model for the specific role. Maybe you want one model for the announcer and a totally different one for generating background visual effects. It's all about availability over hierarchy. This literally frees creators from vendor lock-in.
So, what does a pluggable adapter actually mean here? Basically, it's a unified in-process ComfyUI interface. Think of it like a standardized contract. As long as a new AI model can conform to a simple 5-method contract, handling things like prep, rendering, and teardown, it can just drop into the workflow as an equal peer. It's exactly like an open audition process. Any actor, or in our case, any shiny new AI model, can just step onto the set and seamlessly take over a role. It's a real game changer for flexibility. Section 4 brings us to the 3 core pillars. These are the distinct departments of our studio. Okay, to prevent our laptop from literally melting down, the whole architecture is split into 3 highly distinct silos. Subproject A is the video platform itself. This is the main spine, managing orchestration, the timeline, and the 2D video adapters like LTX or WAN. Then there's Subproject B, which is entirely dedicated to the 3D character stuff. It handles all those complex tasks, like taking a 3D mesh, wrapping it in ARKit topology, and driving it with audio so the character actually talks. And finally, Subproject C is Image Gen. This sits upstream. It uses heavy models, like Flux, to generate the initial base images and portraits that feed directly into the other 2 pillars. The key here? They operate in total isolation, but they connect through strictly enforced data contracts.
So let's move along and see how this actually builds into the canonical lifecycle for an episode. Step 1, the script and frozen audio lock in the timeline. Step 2, a metabrief automatically derives all the rich creative prompts, meaning you don't need to do manual prompt engineering for every single shot. Step 3, Subproject C takes those and generates the foundational images.
Step 4, subprojects A and B grab those images and the audio and render the actual video clips. And finally, Step 5, the system stitches the whole thing together. It is a perfectly sequenced, automated assembly line.
Moving into Section 5, beating the hardware limits. This is all about engineering within a strict 14.5 gigabyte VRAM ceiling.
We've got massive image generators, 3D mesh creators, and video diffusers all at play here. And if they breach that 14.5 gigabyte ceiling, bam, the whole platform crashes. Notice the execution environment column right here. Standard video models like LTX run normally inside the main ComfyUI graph. But, and this is a huge but, the heavy 3D engines, like Hunyuan 3D and Trellis, run in an isolated sidecar. Because they have these massive conflicting dependencies, they're spun up as separate, isolated background processes with an even stricter 14.0 gigabyte budget. They do their heavy lifting, pass the final file back to the main program, and shut completely down. This brilliantly avoids the nightmare of dependency hell. But honestly, isolation just isn't enough on its own. You need aggressively smart memory management. And this brings us to the platform's ultimate survival mechanism, the strict teardown rule. If one model provides a base clip and another model needs to consume it, say to add lip sync, the system physically forces the first model to be completely flushed and detached from the GPU memory before the second one is even allowed to load. They are never, ever co-resident in memory at the same time. This constant sequential loading and flushing, it's quite literally the only way a 16 gigabyte laptop can chew through an entire AI video pipeline without catching fire.
Finally, Section 6, the final assembly. Stitching it all together with Mux Last.
All right, with our zero-waste clips all rendered out and our memory completely pristine, the assembly phase kicks in, and it follows a really strict Mux Last rule. First, a neat node called Silent Composite takes all the rendered clips and stitches them into a single, perfectly timed but completely silent video file. Next up, upscaling and processing are applied to those silent visuals. Then, at the very end of the chain, the Master Audio Mux steps in to permanently embed that original frozen audio track we talked about earlier. The system actually runs a mathematically precise check right here to ensure the video perfectly matches the audio duration. The audio stays completely untouched until those final seconds, guaranteeing it remains pristine with absolutely no re-encoding degradation whatsoever.
And there you have it. That is the architectural blueprint for the OTR Open Video Model Platform. It's a massive testament to what's possible when you combine extreme hardware constraints with incredibly disciplined model-agnostic software design. So I want to leave you with this question. As offline engineering successfully beats monolithic cloud limits, what will you create when you have a zero-waste multi-model Hollywood studio running locally, right there on your laptop? The barriers to high-end AI video creation are dropping fast, folks, and the future is sitting right there on your desk. Thanks for joining me on this explainer, and keep learning.